Okay, I hope you can hear me from the Zoom side. I'm gonna lose my glasses in a few seconds. Okay, so well, first of all, thank you to the organizer for allowing me to give this talk and allowing me to be in the not correct section, because I mean, I probably could have been a better fit just after Francesco, but I was unable to join the conference in that moment. What I'm going to talk today is a realization of a composite Higgs model, and it's a sort of long-term project we have been pursuing with Vincent Drach, Patrick Fish, and Fernando Romero Lopez. And it is about trying to discriminate sources for electroweak symmetry breaking pattern and realizations. And maybe we can move on. Too much. Can you come back, please? Okay, so what we know is that LHC is entering, well, it has entered the stage of run 2. And which are the aims? The aims are to study the properties of the Higgs boson, and in particular, to measure the vector boson scattering. Why is this interesting? Well, the vector boson scattering is going to be a perfect chance to probe the structure of the electroweak interaction. And it's claimed to be extremely sensitive to the new physics. Now, quite likely, Francesco told you already everything about this, but let me point out that is exactly where we expect to find signs of new physics. Now, in the context of physics that is aimed at explaining the electroweak symmetry breaking pattern and its dynamical origin, composites are a candidate for strong dynamics that could be able to describe beyond the standard model physics. And in particular, this composite dynamics is going to be characterized by a strong sector that will contribute to the processes that are at the moment investigated at LHC. You know already everything about composite Higgs model, as Francesco told you, but anyway, let me give you my take on it. And it should not take long, and I will give you a sort of nutshell introduction to it. Which is the idea? The idea is that you have the standard model particle with the Higgs, but these Higgs, and actually also the zeta, Z, and W, emerge as meson from an additional sector. This additional sector is a strongly interacting sector. Now, a composite Higgs boson can arise in various ways, either as a pseudo-Nambu-Goldstone boson or as a light resonance. And this is based on how the condensate aligns or misaligns with the electroweak gauge symmetry. In particular, we have a parameter that allow us to understand whether there is or not an alignment. If you call F the Higgs decay constant and V the electroweak scale, the ratio between the two is the parameter that is of interest for you. In particular, if V is very far smaller than F, you are in a pseudo-Nambu-Goldstone boson setup. Otherwise, when V is of order F, you are in a light resonance-based case. Now, what we know about this new physics is that this sector in isolation reminds us very much of QCD. So, I mean, I'm talking of QCD in some sense, a strong theory that very often realize something that resembles QCD. In other cases, it does not resemble at all QCD. However, notwithstanding the fact that it looks or not like QCD, no matter what, there's going to be a strong interacting sector with a flavor singlet state. This is inevitable. In QCD-like theories, this sigma, this flavor singlet state, is a resonance of two Goldstone boson in the limit for the underlying fermions to be massless. Instead, in our identification for the composite Higgs model, this sigma is going to affect the Higgs as the same quantum number. It has to couple to it, it can mix to it, or it's going to appear in the hunt of the Higgs. So in general, I cannot tell you exactly which of these scenario is going to be realized, because it's going to depend on how we imagine to embed the additional strong sector into the pattern of the electroweak symmetry breaking. So it will really depend on the embedding. However, what I can tell you for sure is that this additional sigma state is going to appear and is going to have an effect on us. Now, the phenomenological perspective is that this 0++ state will mix with the Higgs boson. How much, I cannot tell you, it will depend on the embedding. And it is expected to show up at LHC as an heavy resonance. It's going to be produced exactly like an Higgs. So it's going to be produced via gluon fusion. And depending on the embedding, we'll have different phenomenological implications. Now, in the following, I'm going to think specifically about one realization based on theories that are SU4 broken to SP4. These have been exactly described in this paper, and all the phenomenological embedding are there described. In particular, I find them extremely interesting because they have, okay, that chiral symmetry breaking partner. They are a new ultraviolet completion of a minimal composite Higgs model. So they are an embedding that are well defined. In this specific embedding, the Higgs turns out to be a linear combination of the Goldstone boson and of the 0+ state, 0++ state actually. And what is extremely interesting is that it's not yet ruled out. I mean, in the end, here the game is to give a good handle, a good smoking gun to say, yes, we can do it, what we cannot do it, and how to describe or contain the freedom of choosing this additional parameter. And what I'm gonna try to convince you is that having a control over the sigma has a very powerful effect. Now, unfortunately, you have to bear with me for a couple of moments of group theory, because the breaking of this SU4 coming from SU2, so this enhanced symmetry, is a bit cumbersome. So how do we create a flavor singlet quantum numbers from these states? It needs a couple of minutes of concentration. So first of all, we rearrange our fields. U and D are usually SU2 fields, and we arrange in this multiplet that here is described. What is interesting is that in this multiplet, the fact that we have an SU2 that is a pseudo-real regeneration allow us to expand the symmetry and to explicitly prove the break into SP4. It is a bit of a group theory exercise, but what you can show is that if you reorganize your fields in this way, every single bilinear written as pi, so pi, trace of pi, or sigma, is a singlet, a singlet for the flavor quantum number. So it's a flavor singlet quantum number. Now you can also re-express this field in terms of the usual pion or baryon that we are used to in our QCD-like theories. And what you see is that some strange fields that are di-baryon due to the fact that we are in SU2 appear. So we have our usual pionic degrees of freedom, or pseudo-pionic, in the sense that these are pion on this strong sector, but there are also these strange capital pi, or how we call them, di-baryon states that are part of our base. Now you can create your singlet operators just by taking trace of two of them and rewrite the original SU4 multiplet in terms of our QCD-like fields. You can do this with the capital Pi, or you can do directly with the scalar, such that you here contain the Goldstone boson and here contain the sigma state. Fantastic. So we have our operators, but what do we do? I mean, there is a leap of faith here, because in our lattice simulation, we have no idea of how to understand how to mix these states and how to understand whether or not we are dealing with a resonance, a bound state, what is a scattering. We are working in a setup that is Euclidean, and studying a scattering in such a setup is not trivial. Indeed, for scattering states, allowing just the allowed, studying just the allowed energies is not sufficient. You will end up describing states that are above the threshold of 2 of the lightest degrees of freedom of your system, and you cannot describe whether the system is really a scattering state or whether it exists or will decay. You are moreover in a setup that is Euclidean, so you don't have temporal evolution to understand what's the fate of these states. So you have to reside and turn around your game and think of a different way. Now, the physical information of the states that you want to study is encoded in the S matrix. If you imagine to be able to study the S matrix has a set of beautiful properties that go from unitarity to the fact that it's a block diagonal for the angular momentum. And you will encode all the relation among the interaction of the particles that are at the basis of your scattering theory. Very good. This is more or less a textbook, because this interpretation dates back to many, many years ago. However, let me just mention, for the sake of what is to come, that I will represent my scattering amplitude, for example, in L equals 0 in terms of this phase, or actually in this specific way with the matrix M. That is a real function that contains the scattering information. This is a usual setup. Now, how do we pull out what happened here? Something disappeared. Okay, very good. Okay, better. Sorry. How do we come out with information about scattering? Well, it's a very nice setup and interesting method that has been used now for many, many years. If you put your system in a box, your system will have a memory of itself. So the states will interact with themselves and leave an imprint in the lattice. In particular, they will change their energy of states energy, the tower of the energy states. And by the change of the energy states of the entire tower of spectrum, you will be able to read how the properties of interaction can be described. A typical example comes from, from the 58, from Young. Indeed, he managed to say that for a weakly interactive two-body system, the information of the scattering amplitude, that is exactly the matrix M that I am described, that here is parameterized by the parameter A, can be extracted by the finite volume ground state behavior. If I look at the finite volume ground state, I put my system in a box with extent L, the coefficient of the scaling in L cube will give me the information of the scattering amplitude. So this is a very powerful tool. The information that I was unable to come out with from the usual analysis is encoded in the finite volume. Now, this information has been extended and studied in many, many papers. First of which is from Lusher and then extended to interaction of many, many particles, 3 particles, and is an ongoing story, but is encoded in this beautiful and terrible equation. M is, I mean, there's nothing I can say about that. M is a matrix that encodes the scattering amplitude, as I've described 1 moment ago, and F is a set of known geometric functions. These have been expressed for 2 by 2, 3 by 3 over the years, and more spin states, but is something that is fantastic if your life is easy. Indeed, your life is easy if you are in S-wave, because a matrix that is a scalar drops the determinant, this becomes an equation, and your life is simple. So the beautiful quantization condition that I've written before becomes just a simple equation if you are in S-wave. The equation here written gives me the condition under which I am sure to find a bound state. In particular, kappa here represents the momenta of the 2GB, the Goldstone boson in the center of mass frame that is obtained from the energy level. Z00 is a zeta function known as a geometrical factor. And I can describe a bound state condition when I cross this line. If I cross this line from below, I have the certainty that I am creating in the lattice a bound state. Fantastic. So I grab all this knowledge and all this machinery, and I go to see if my beautiful sigma is or not creating a bound state. And if I can give information to my friends, the phenomenologists, to say, okay, let's cut out some of these models, or let's constrain the parameter search space. Okay, we started with our simulation details, and we have used IREP to measure what is here described. I mean, for the sake of description, this is a improved Wilson action, or the improved Wilson action with 3-level semantic for the gauge. What is interesting to notice here are the mass of the pion and the mass of the rho. Now, if you notice here, I will have that the rho is always heavier than twice the pion. This is interesting for the future. And MPL, the extent of the box, is large enough not to suffer from too small boxes. Now, the contraction, unfortunately, this is another moment of pain for all of us. They are awful, because the contraction that give rise to all the possible interaction of the terms that are isosinglet, each single one of them contain what we call disconnected diagrams. So there's not much to say about that. Our life is as tough as QCD, if no more, because in this case, each single term of this correlation matrix that I'm going to study contains a disconnected diagram. Life is tough, okay, but we go on with that. So we measure the constant contribution, we measure the correlator coming from pi pi to pi pi, pi pi to sigma, sigma to sigma. And each one of them has a disconnected contribution. We fight very hard. All the details of the battle will not be here with you. Otherwise, they make even less interesting the discussion. But what we see is that we can follow our correlator for quite a while, so that we can evaluate the eigenvalues of my system. And we can see that, first of all, I'm capable of making a good fit of the eigenvalues and determine the energy over the mass of the pion for the two ensembles, for what I call the heavy ensemble and for what I call the light ensemble. And what is interesting here is that these masses are below the 2 pion threshold. If you want, this is the bad news. Indeed, I can finally start to produce my scattering amplitude, and my scattering amplitude here, so represented in the kappa cotangent delta representation, are this one for the low eigenvalue, and this one for the high eigenvalues. I hope you can see the mouse, for the heavy ensemble and for the light ensemble. Here the shadow and this pole is totally an artifact of the fact that I am inverting the kappa cotangent delta function, so there is a 0 in the inversion. There is nothing to worry about. In particular, however, you can see that the errors are large. However, what I can immediately quote is that, if you remember, I described the condition under which I can have a bound state. The condition under which I have a bound state is if I cross this line from below. And our data seem to suggest that we are in a position for which we can say that there is a bound state. However, can we trust our data? Can I grab this data and start to say, okay, I can extract now, for example, the scattering amplitude and give it to my friends? Well, there are a number of caveats in these numbers, and I want you to notice. What we did is to say, let's assume that everything is working. If everything is working, I can go in chiral perturbation theory and make a representation of my data. If I go in chiral perturbation theory and make a representation of my data, I expect that my data describes a bound state that crosses the bound state constraint, the bound state condition as described by the continuous curve. We seem to be very, very far away from chiral perturbation theory. Indeed, keep in mind that we are below threshold or above. So we didn't fulfill the threshold at the moment. So what we think is that, notwithstanding the fact that we are capable of expressing a good bound over the scattering amplitude, the picture that we are describing could change should we send the pion lighter. So if you want, this is an ongoing project. Because I am already reaching my conclusion, we have studied the singlet channel. However, notwithstanding the fact that the results are compatible with a bound state in the singlet channel, we will not quote these immediately for our friends, the phenomenologists. The more point is that we may need a more chiral setup, because a more chiral setup could, quite likely will, change drastically our understanding of the scattering amplitude. And a continuum limit is anyway needed. However, we are describing of a long-term project that is as tough as QCD. Let me point out, this is the first computation ever done for a singlet channel in a theory that is not QCD. So in some sense, what we are starting to see in this moment is that some of these results are getting terribly hard, and there's no way around. We need to fight hard in order to obtain something that is of phenomenological relevance. So with this one, I thank you very much, and I'm happy for questions.
Thank you very much. Are there questions or comments?
Yeah, I just wanted to know, Antonio.
Yeah, it's terribly hard. I mean, in QCD, we know very well that being able to reach this threshold means that you are capable to lower the mass of the pion below the. So let me say this again. There are stability issues with the algorithm of generating this configuration. And when you go to pion that is light and twice the rho, you start to see instabilities in your code, and the code starts to be extremely expensive. How hard it is? Without, well, in the setup in which we are, without the use of smoothing techniques, we are unable to reach the threshold. So practically, the kind of action that we need to use is already at the level of what I would call a cost comparable with a 250 MeV pion for QCD. Just rescaling to comparable costs. QCD is harder because it has multiple scale, because we are in some sense in an easier setup. We have just two light degenerate flavor. Yet the instabilities are there. So the zero modes of the Dirac operator, in particular because we are dealing with the Dirac-Wilson fermion setup, are there. So I will not tell you that it's as hard as QCD for the time being, but it's getting harder.
Thank you. Any other questions? Oh, there's a question online. Gunnar, please.
Yeah, so thank you for your nice talk. Of course, I'm more familiar with SU3 with NF equals 3 flavors. And of course, the analogy is not complete, otherwise you wouldn't be performing your simulations. But in that theory, if I have a pion mass that is 5 times heavier than the pion decay constant, that is a pretty large pion mass. Do you have some idea how far away you are in the Carrel limit? For example, if you compute it in units of the T0 scale or some other pure gauge scales?
You are absolutely correct. I mean, we believe to be still pretty heavy. However, in the rho pi channel, the study that has been done, as I said, the rho is lighter than twice the pion, and the description of chiral perturbation theory is decent. I will not call it adequate, but at least decent. So translating this from our understanding of QCD may be misleading. At least chiral perturbation theory for the rho channel seems to be not too wrong. Clearly, in this other channel, we seem to be heavy. And so we believe that we need to go lighter. How lighter, I cannot tell you in this moment.
You also mentioned these algorithmic instabilities. Are you planning, or have you been doing this exponential Clover term? Would that help there a little bit?
Yes, the next run, the one that are ongoing, are exponential stabilized, and are already, well, they are already capable of reaching far lighter mass of the pion. However, as I don't have any result for the measurement of the scattering amplitude, I will not tell you. I cannot tell you anything about that. However, we are already capable of reaching a way lighter mass of pion.
Okay, any other question? I don't see any more questions, so then let's thank Antonio again.